Hello and welcome everybody. We're so excited that you joined us today, January 18th, for the Zoom call with two prominent NASA engineers, scientists. My name is Kelly, and I am the CSO International Director. And on the call hosting tonight is CSO Austin from Penridge High School in Pennsylvania.
Hi, everyone. My name is CSO Chalet, and I'm on the CSO International Leadership Council. I represent the state of Arizona. And I am on the call tonight because I've been lucky enough through the CSO program to visit NASA headquarters a couple of times. And that's actually where I want to work one day. My dream job is to be an astrophysicist at NASA. So I'm super excited to hear from you two tonight.
Tonight, we want to make sure that we have a chance to get to know our presenters, and then we're going to have a Q&A session directly about anything that they shared. They are willing to stay longer if you have more questions, so please be active in the chat box. And I'm going to send it over to Austin to share what exactly he has in mind for tonight.
Good evening, everyone, and welcome to a special CSO Zoom In on Science Call, NASA edition. I'm Chief Science Officer Austin from Pennsylvania, and I'll be hosting the Zoom tonight. But you're not here for me, you're here for our esteemed guests from the National Aeronautics and Space Administration, right? So let me introduce Mr. Henry Throop and Mr. Bob Collum. Thank you both so much for joining us tonight, and we all look forward to your presentations. But first, for some further introduction, our first presenter, Henry Throop, is a planetary scientist and astronomer for NASA, where he manages NASA's scientific research programs in the outer solar system. He was a member of NASA's New Horizons mission and co-discovered Pluto's smallest moon, Styx. Also, he has won the Carl Sagan Medal and literally has an asteroid named after him, of which I can think of no higher honor. Also joining us is Mr. Bob Collum. Bob has been a member of the Mars Recon team and is an integration lead for science and exploration. He was a project lead for the 2020 Mars rover naming contest, in case any of you entered in that. And he participated in the International Mars Exploration Working Group with 25 other member nations. All right, so both men will present their slides and give presentations, and then at the end we'll do a Q&A session, so make sure you think of some good questions along the way. Without further ado, Henry, please take it away.
Thanks, Austin. It's awesome to be here. I'm going to share my screen here and talk a little bit about the New Horizons mission to Pluto. Okay, can you see my slides there? All right, so first, just a little bit of an introduction about myself. I'm wearing a suit. I'm not wearing a spacesuit. I don't have a spacesuit. Plenty of people ask me as an astronomer how often I go up into space. The answer is never. It's because I'm an astronomer. I use telescopes and spacecraft to study the solar system from the ground. Most of my time, as I spent in front of a computer on telecons, writing code, analyzing data, emailing with my colleagues, and so forth. I have spent plenty of time observing from telescopes around the ground, around the Earth on the ground. Here's one telescope in South Africa that I was using. And I've also used large telescopes in other places around the world. Just a little bit of background on me. I grew up in Oregon. I spent lots of time I really had a great physics teacher in high school there. Loved physics as a result there. I did lots of science fairs, things like that. Built some airplanes, built some other science fair projects. I went to Grinnell College in Iowa. I studied physics there for 4 years. And then I went to University of Colorado to get a degree in astronomy. And in 5 years, I got a PhD in astronomy. And this is really fun. Grad school, 5 years seems like a long time to be in school, but the point of being in grad school is that it's really, you get to be an astronomer for that time. You get paid to do great work and learn about the solar system and use telescopes, write papers, and be the world's expert on your field. So it's really a fun way to spend 5 years. Since I graduated, once you have a PhD in astronomy, you can kind of do whatever you want to do in terms of research or working at an observatory or working at NASA or whatever it is. I've lived all around the world doing astronomy in India, Africa, Mexico. Now I'm living in Washington, D.C., where I'm running science programs at NASA headquarters. And I've been doing that for a couple of years. So I want to talk just a little bit about this New Horizons mission, which went past Pluto a couple of years ago. And just to put it in context, here we have our galaxy. Our galaxy is 100 billion stars. Our sun is just one of those stars in the galaxy. We have our sun at the center, and then outward we have Mercury, Venus, Earth, Mars as the rocky planets toward the inside of the solar system. We have the gas giant planets, Jupiter, Saturn, Uranus, Neptune. And then out beyond those, we have the icy planets, which starts with Pluto and then goes into the Kuiper belt. And you can see many of these just from your with your naked eye. Many of you saw the conjunction of Jupiter and Saturn last month. This is, I used to live in Bombay, India, and this is just a picture from our house there. And you can see with your naked eye, you can see the Earth, Sun, Moon, Mercury, Venus, Mars, Jupiter, Saturn. You can see most of the solar system with your naked eye. What you can't see with your naked eye are the really small or distant things like Uranus, Neptune, Pluto, and the asteroids. So in 1905, the first history of Pluto, in 1905, this guy named Percival Lowell, he started looking for what he called then Planet X, X just being the unknown, Lowell Observatory, which he named after himself. How thoughtful, in Arizona. He looked around, he couldn't find Pluto. Then eventually he hired someone else to look for Pluto for him. This guy named Clyde Tombaugh, took the train across the US and ended up going to Arizona to help him look for Pluto. He used this telescope here. And this telescope, he used a cool little trick to use this telescope to look for Pluto. And I didn't know where Pluto was, but he did know, well, you know how you have the constellations in the sky. And you have like the Orion rises every day and then sets, and it has a pattern in the sky that it makes. With Pluto, same thing happens, that as it rises in the sky, then the stars around Pluto rise and they set every day, and they don't change their position. They don't change their shape, or the constellations relative to each other. And so if one of the stars moves, you know it's something which is not a star. In this case, it's Pluto. So what you can do is you can take pictures of the sky and then look for something which is moving relative to those fixed stars in the background. So what he did is he used that telescope there, and he took pictures of the sky one night and then came back the next night, and he did this night after night. And this is a set of two pictures right here. In fact, if you look closely, you can see one of these stars which is moving. I'll circle it. It's right there. And it moved to a week later, it moved to over here. Boop, 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 boop. So right there, that's the very first image of Pluto that was ever taken and noticed. So that was back in 1930, the first discovery of Pluto. There were later images that were followed up with that. This is a picture zoomed in of Pluto here. You can see Pluto's the big blob in the center. And if you look really closely, there's kind of a blob on the side of that blob, which moves. This is images taken in 1976. And what we inferred that this is actually Pluto's moon, and it kind of was rotating around Pluto. And 3 days later, it wasn't there anymore, and that's because it was rotating around to the backside of Pluto. This is 1978. A guy named Jim Christie used the telescope to discover Pluto's moon, named Charon. So now we can take better pictures of Pluto. Like this is a picture taken with the Hubble Space Telescope, but this is actually about the best picture you can take with a Hubble Space Telescope. And Pluto is really just like a pixel or 2 pixels across. It's pretty fuzzy blob. There's nothing you can really see on the surface there. You can see its moon Charon over there. We've used Hubble to take some better pictures. Here's a picture that we used to discover 2 more moons around Pluto called Nix and Hydra. Here's a discovery, another moon called Kerberos. We discovered in 2011. And then I was part of the group that discovered this moon named Styx around Pluto in 2012. And it's hard to see, but I promise you that it really is there. And so as of a couple years ago, if you took everything you knew about Pluto, you could put it on one slide here. You know basically how big it is, you know, from the laws of physics, how long Charon takes to go around it, so you can use Newton's laws to figure out how big Pluto is and its density, and a little bit about its composition. We know it has a little bit of atmosphere. It has all these 5 moons going around it, but not much more than that. So to know anything more about Pluto, you need kind of a close-up visit. So this is kind of cool. You know, if you're studying stars, you can't really get very close to them. If you're studying galaxies, you can't get close to them. But if you're studying things in the solar system, you know, you can build a bigger and bigger telescope. That's how you can study things like a galaxy. You have to build a bigger and bigger telescope. If you're studying Pluto, however, you can have a little shortcut. You just take a small telescope and you fly it to Pluto. And so that's what we do at NASA. NASA's exploration of the solar system is mostly focused on building spacecraft which go through the solar system and take a small telescope and land it on that planet, or orbit that planet, or in this case, fly past the planet to study it that way using a small telescope rather than using a bigger and bigger telescope from the Earth. So this is the New Horizons spacecraft. This is what we have, which launched from the Earth in 2006. It flew past Pluto in 2015. It's about the size of a piano. There's no people on it. This is not a human spacecraft. This is a robotic spacecraft. It flew past Pluto, took pictures, and then sent them back over its radio. And if you look at it, it's kind of got 3 things on it. It's got a battery, it's got a radio, it's got a camera, a couple of cameras. What else has a battery and a radio and a camera? It's basically your iPhone 12 Pro here with slightly we have a better battery than the iPhone does for sure. We do not have as many pixels as these fancy cameras on the iPhone, but we do have some of them which detect different wavelengths than the iPhone detects. And then so basically we take pictures, click a picture of Pluto, and then send it back over the radio link. But conceptually, it's exactly the same as a smartphone. So here's an actual picture of the spacecraft itself. We've got a big old radio dish on top, which is what we use to send images back. We have down at the bottom, we have all of these cameras. We have about 5 different cameras on here, one in the infrared, one in the ultraviolet, and a couple in the visible. And then we have some other detectors like of the solar wind and things like that. So we were selected by NASA in 2001. We were selected by NASA in 2001, and it took us a couple years to build the spacecraft. It took us, go ahead. Oh, there we go. Here's some pictures of just building the spacecraft. This is built in a lab outside of Washington, D.C. at the Applied Physics Laboratory at Johns Hopkins University. Here's some of the spacecraft engineers with their baby here. This is pre-coronavirus. That's not where they weren't wearing the masks. And it takes a big team to get these spacecraft off the ground. I'm in the back there. We're in a blue jacket there in the far right-hand corner. But there's about 2,000 other people who have worked on this mission. And some of them are scientists, some of them are managers, some of them are writers, some of them are educators, some of them are software people, some of them are machinists, some of them are hardware engineers. There are so many different people. There's kind of a job for everybody on this mission. And the actual people who are astronomers on this mission is a relatively small fraction of them. Maybe 1 person out of 10 is an actual astronomer working on the mission. There's a lot more engineers, a lot more software people, a lot more IT people that it takes to get everything going on this mission. So this is a relatively small mission in terms of NASA missions, but it does take people from every field, both science and non-science, to get these missions going. Right at the center there is Dr. Alan Stern, who's our principal investigator. He's the one in charge of the whole mission. We built a lot of the spacecraft in Colorado. Other parts were built in Texas. Other parts were built outside of Washington, D.C., and we took it down to Florida to launch it. This is in 2006, January 2006. In fact, it is 15 years ago tomorrow that our launch was on January 19th, 2006, when our launch was. So 15th anniversary coming up tomorrow, really cool. The area of the spacecraft is in the nose cone up there. Basically, the trick here to go into Pluto is that we had the biggest rocket we could buy and put the smallest spacecraft we could on top of that. That's how we got to Pluto in 9 years. Pluto's 4 billion kilometers away. It's a long way. That's the furthest we'd ever sent a spacecraft to its target out in the solar system. And so you have to go really fast to get up there in any sort of reasonable time, like before everybody dies. If you put a big spacecraft there, it's just conservation of energy. It's going to take a long time to get out there, and you don't want that. You want results before the end of time. So the rocket is, if you work out the physics of how the rocket equation works, you have to use a lot of fuel to get something which is even tiny out there. What we have is about 40 kilograms of instruments. That's what we're really trying to get up to Pluto. With the spacecraft weighs a couple hundred kilograms, and then it takes 600,000 kilograms of fuel to send all that spacecraft out there at it goes about maybe 20 kilometers per second when it's going. The launch vehicle goes for about 40 minutes, and then it disconnects. So that most of the cruise to go out to Pluto is unpowered, just like a bowling ball. You push the bowling ball in the right direction, and once you push it in the right direction, it keeps on going. Just momentum keeps it going, and that's the same thing that kept our spacecraft going through the solar system. So we assembled in 2006, got ready to launch this. Everybody watched it. It's really exciting. We're down in Florida. Here's a spacecraft. It's going off. It went off on the 3rd try. We had some problems with wind on the first day and rain on the 2nd day, and then on the 3rd day it went off beautifully. It's so much fun. Here's watching it go off from the beach. Really an emotional time, because this people have been spending the last many years of their life. It took about 4 years to build this spacecraft and get it flying. So it's pretty much a straight line trajectory to go out to Pluto. We did fly past Jupiter. We flew past Jupiter about a year after launch, and then it took us 9 more years, 2008, 9, 10, 11, 12, 13, 14, 15, until we got to Pluto. Here's a map of the solar system. It's pretty easy to get through the solar system. In fact, it's a lot easier to fly through the solar system than it is to drive through like the streets of Toledo, because there's a lot more things you can hit when you're driving through the streets than there are things that you can hit when you're driving through the solar system. You just point yourself in the right direction. Space is pretty much empty. We're not going to hit an asteroid. We did cross the asteroid belt, but you're not going to hit an asteroid. You could go back and forth between the asteroid belt like millions of times without hitting anything. It's not like that scene in Empire Strikes Back. So we flew past Jupiter. We got up to Pluto in 2015. So flew past Jupiter, took some great pictures of Jupiter. This is the highest resolution global image of Jupiter that had ever been taken at the time. This is so cool. This is one of Jupiter's moons named Io. This is a little time-lapse movie of a volcano going off on the surface. Io is so cool. This is totally unexpected. We've never seen a volcano actually in action on the surface of Io before. And then we had our cruise. It takes 9 years to go out there. What are we doing? Are we just hanging out? No, basically, we have one chance to go past Pluto successfully. And so we wanted to do everything right. So we had lots of dress rehearsals, lots of planning the encounter. So we were not landing on the surface of Pluto. We were flying past Pluto. And we weren't even orbiting Pluto. The reason was, you might be like, well, that's stupid. Why don't you want to orbit Pluto? We did want to orbit Pluto, but you can't do that because we were going so fast. Remember, Pluto's 4 billion kilometers away. We were going really fast. And so in order to orbit Pluto, you'd have to slow down. How would you slow down? Well, Pluto doesn't have enough gravity to slow you down. And also, you don't have enough fuel on board to slow yourself down, because to take all that fuel, like that would double the size of the spacecraft, and we couldn't do that because that would mean we wouldn't have any room for instruments. So what we had to do is just fly past Pluto and do that really quickly. It's the only way to do this mission. It's not really possible to do it with an orbiter. We spent this 9 years practicing and basically doing it so we wouldn't screw up our encounter with Pluto, doing dress rehearsals, testing, optimizing our science, because we knew we had just one chance to do this and we had to do it right. What was my job on this mission? Before we launched, I was working on the infrared spectrometer. I was working to calibrate that and get it ready for launch. I was working during our cruise, developing a lot of software tools to plan the observations. I was looking for dust, which might be a hazard to the spacecraft. That's because we thought there might be dust rings around Pluto. And I said that space is pretty empty, but that doesn't mean that the area right around Pluto is empty. We thought there might be dust, which was kind of orbiting Pluto, just like all those moons are orbiting Pluto. We kept finding more moons like Styx and Nix and Kerberos and Hydra. We kept finding more moons. We thought there might be dust there too. So we wanted to search for dust and make sure that we wouldn't, at the speed that we're going, even if we hit the spacecraft with just something the size of a grain of sand, it could be the end of the mission. And then I was setting up a lot of our observations for looking for rings, searching for new moons, things like that. And then I was involved with the encounter itself, looking for new moons and looking for rings. So as we got to Pluto, we weren't observing the whole time because 9 years, and we just had a small telescope. Like, our telescope was not the size of the Hubble Space Telescope. Our telescope was the size of like a backyard telescope you could buy for a couple $100. That's the one that we put on the spacecraft. So it's about 8 inches across. Some of you might have used 8-inch backyard telescopes before. And so the advantage of having this small telescope is just that you can take it to Pluto. So most of the time we weren't observing Pluto this whole time during this 9-year cruise. In fact, we really only turned it on and started observing Pluto in the final year after we were gone flying for about 8 years. So we turned it on. Here's the first good image that we released from of Pluto. And you can see that it's kind of a fuzzy blob at that point. It looks kind of like those images from the Hubble Space Telescope. And then we're getting couple weeks later, we're getting a little closer. You can zoom in, you can see a couple of pixels there, couple of pixels here. Now I can see Pluto and Charon orbiting each other, really cool. Getting closer, June 27th. Closer every day. Oh, then it stopped. We were broadcasting data to the spacecraft and listening for it to respond to us, and suddenly our carrier signal was lost. We couldn't find the spacecraft anywhere. We looked around for it. This is on July 4th, 2015. The spacecraft had vanished from the control room. So we have big antennas on Earth that we use. These are the largest steerable antennas on Earth. They're 80 meters across. And we were like, what's happened to the spacecraft? It's all gone. This is about a week before encounter with Pluto. And so we called up the antenna people and we're like, hey, did your antennas just break? And they were like, nope. And well, is there a rainstorm? Because that can sometimes block the signal. That didn't happen. And so we weren't really sure what happened to the spacecraft. We looked around for it. About 3 hours later, we found it transmitting on a backup frequency. It had just rebooted and it was confused and it was lost. And so we have about 10 days here until our mission encounter with Pluto, and our spacecraft is confused and lost and doesn't know what's going on. So we put the spacecraft in what's called safe mode. This is kind of like what happens with, if you're with a friend and, you're out somewhere and, you're with your friend and you're lost, and then you text them and like, yo, man, where are you? And you might text back and forth to eventually figure out what's going on. But keep in mind, with our spacecraft, it takes 4 hours to send a message to it, and then it has to think about it, and then it has to send the message back to us in 4 hours. And so we didn't want to go back and forth too many times with this. So we figured out pretty quickly what was going on with it. There was a software issue. Alice Bowman, who's the head of our operations, figured out what was going on with it, her and her team. There was essentially a software bug. We overloaded the processor on it. And if we wanted to have fixed it up, we would have flown past Pluto at 20 kilometers per second and lost the entire mission. No way to turn around, no way to take any images. It would have been a completely lost mission. Luckily, she's awesome. Her team is awesome, of operations engineers. So we figured out what was going on. We rewrote the system software. We tested it all on the ground. And then from 4 billion kilometers away, we reprogrammed the whole spacecraft. 2 days later, we were back on track, and the spacecraft continued, started getting that data back down. So here we go. We're getting closer and closer to Pluto every day. Got on the final day that we actually fly past Pluto, we receive our. So here's what's going to happen on the flyby day. 3 o'clock in the morning, we get our highest resolution global images of Pluto. By 8 o'clock in the morning is our closest approach to Pluto. It doesn't send back all those images quite in real time because it takes 4 hours to send them back. And also, it's just like if you take 1,000 pictures and you just have like 1 bar of signal, right? It's going to take you like a week to send all those images back. Well, for us, it took about 2 years to send all the images back. So the spacecraft can't even send images back when it's looking too, because it can only do one thing at a time. So it was taking its time to just observe Pluto on this global day, this golden hour of the spacecraft. And but we did take a break from its observing one time at 8 o'clock in the evening, which is to send us a little signal saying, hey, I'm alive, I'm awake, I'm okay, I've taken pictures. So here's the team at the hotel. We have like 200 astronomers hanging out in the hotel and engineers hanging out in the hotel. On the day of encounter, when we first get to Pluto, this is 6 o'clock in the morning when we're all poised here, ready to see this first image that came down from Pluto. You want to see the image? Let's see our first global image of Pluto. Here we go. So this is the image that came down, and this is just totally stunning. We had no idea what this would look like, and here is Pluto. So what we see here is that Pluto's it's not like the moon. This is real color. This is basically what you would see with your eyes. It's brown, it's yellow. It has some regions which are darker, some regions which are lighter. These are all made of ice, and it has a little heart on it because we love Pluto and Pluto loves us too. So this is all the scientists, all the engineers who have been spending the last 9 years of their life planning for this encounter, sequencing the observations for it, testing the observations and so forth. Here's all the geologists right there. And then we spent this is the image that we had for one day. Where the spacecraft is off observing Pluto, and then we had this image to look at for the whole day. And I just love this because these are geologists, some of them, and they're just, what do geologists do? They like to find mountains, they like to find valleys, like to run their hands over the terrain and figure out what's going on there with the surface. So that's what we did for a lot of this day, is just explore the intricacies of this one global image of Pluto. Then meanwhile, the spacecraft, it was just off observing Pluto the whole time. It was taking thousands of pictures of Pluto this whole day. And then it was about to send them back to us. We were waiting for it. We were waiting to hear from it. It was supposed to broadcast to us at 8 p.m. And so we're here, we're in this room gathered, waiting with bated breath to hear from the mission. We heard from it, really exciting there. You can see the head of press relations at NASA Science is really excited to get the message back that we heard from it. What's really cool here is after 9.5 years and 6 billion kilometers, we arrived 1 minute early. So navigation through the solar system is pretty cool. But it's pretty easy. It's as long as you point yourself in the right direction, you know where you're going, you're gonna get there because we know where the solar system is. We know where the planets are. So this is a picture. It's like the one before. This shows you the different regions on Pluto, different colors of ice. Some of these regions are organic molecules, not meaning organic like there's life there, but just meaning they're made of carbon, hydrogen, and oxygen. There's some nitrogen ice on there. There's some methane ice. There's some water ice, all sorts of things like that. So I'm not going to go too much into the science here because I want to turn it over to Bob here in just a minute or two here. But I just want to take you on a tour of a couple of these images here. all these plains of ice, just a super, super varied terrain here. What's happening with this ice here, it's probably, we expected to see craters all over the place. And what you don't see here is a lot of impact craters. Like the moon is just covered with craters. We didn't see any craters on Pluto. What we did see is a lot of areas of ice that kind of look like these polygons here. We think what's happening here is Pluto's surface is almost literally boiling, or kind of turning over and convecting. Kind of like if you have a pan of like pudding on the stove, you have these little convection cells where heat is at the interior and trying to escape out. And we think that's what's causing these shapes here. Now it's moving very slowly. Now, on your stove, it might take a couple seconds for that pudding pot to boil over like that. And on Pluto, it takes hundreds of years, thousands of years for this to happen. But it's probably the same process. Probably some heat at the center of Pluto that's trying to escape. We saw these mountains, crazy cool, because these ice mountains on Pluto, I mean, it's 4 kilometers high on Pluto. And Pluto's the smallest planet, but it's got these mountains that are like half the size of Mount Everest on them. So what's going on with those? Totally baffled. We didn't know what was going on there. We got this massive hole there. It doesn't look like an impact crater. Maybe it's some sort of volcano or ice volcano. Not really sure on that. We've got these mountains of water ice that are just poking through all this nitrogen ice. What you see, the big plains there, just made of nitrogen ice. Because if you take the room that you're in right now, it's got nitrogen, it's got water vapor, it's got oxygen. It's got methane gas and so forth in the room and the air that we breathe. But if you take yourself out to, minus 250 degrees, which is about the size, the temperature that it is out of Pluto, then all the gas in the room that you're in right now would freeze out into a layer a couple millimeters thick on the surface of Pluto because it's so cold out there. So all that, Pluto's made of the same stuff that we are. Pluto's made of the same stuff the atmosphere of the Earth is, but it's just so cold out there that everything turns to ice instead of being solid. Pluto's got a moon, its named Charon. It has more impact craters on it. It has this mysterious red stuff on the surface. Toward the North Pole. It's probably part of Pluto's atmosphere, which has gone through space. And Pluto's graciously donated some of its atmosphere and landed on Charon's surface there. It's got this big crack in the center, which kind of looks like the crack you might get from the thermal expansion or contraction of a loaf of bread. Same thing going on there on the surface of Charon. You have these big mountains. I love this picture here. This is just as we're departing from Pluto, where you can see just the varied terrain here. You have these really, really smooth areas, and then you have this really, really mountainous area. It looks like a bunch of cauliflower. And then you look at the atmosphere there, and you have all these layers of the atmosphere. And so Pluto's atmosphere is 100,000 times less than the Earth's atmosphere in terms of density. But you have all this, you can see it right there, and you can see all these layers. And these layers is kind of like looking through layers of geology, strata of the rocks on the Earth, and that's really what you're seeing is the history of Pluto in its atmosphere right there. So Pluto was not the end of the mission. We in fact did go on to something else, which is named Arrokoth. It's a Kuiper Belt object. I have more slides that I can talk about that now, but I think I want to turn it over and move on. And if I have questions later on, then I can talk more about Arrokoth, which is this Kuiper Belt object that we sent our spacecraft back 3 years after Pluto. So I'll end my slides here for now, and then we'll move on.
Perfect. Thank you so much for your presentation, Henry. That was great. All right, Bob, would you like to present your slides?
Yeah, for sure. And this is a great presentation, Henry. One of my favorite things about working at NASA is getting to hear about all the other cool work my coworkers are doing. So yeah, I get to learn about Pluto while on my way to talk about Mars. So yeah, I'm Bob. I work as an integration lead as part of the Mars reconnaissance team at NASA headquarters. We're a subgroup of the Mars Exploration Program. The Mars Exploration Program helps manage all of the Mars robotic missions that are currently out there. So Curiosity, the Mars Reconnaissance Orbiter, all the previous rovers as well, the upcoming Perseverance that's going to be landing in exactly a month, February 18th. And my team is focused on what's next. What are the questions we need to answer, and what's the data that we need to collect before we can prepare to send human missions to Mars. It's kind of the next horizon goal for NASA's exploration efforts. I guess a bit about myself. So unlike Henry, I don't actually have a science background or a hard science background. I grew up in Los Alamos, New Mexico, and I was always really fascinated by space. I loved looking up at the stars. I read a lot of science fiction as a kid, and loved Star Wars, Star Trek, all that. But I was much better writer than I was a mathematician. So when I went off to college, I was interested in political science. I wanted to help change the world, do some good, I guess. But as the more I learned about the field of political science, I felt the fewer opportunities were really all that interesting to me. And it wasn't until my junior year that I discovered the field of space policy. And that kind of perfectly married my interests of, my love of space exploration with my kind of advocacy and policy background. And from there, I spent the rest of my undergraduate degree and into my graduate degree, which I did at American University here in Washington, D.C. And I tried to focus it in on space policy and look for opportunities at NASA that did not require a master's in engineering. Eventually, I was able to get an internship at the NASA History Office, which is a great part of the Office of Communications. I got to do a lot of fun stuff, learning about the shuttle missions and everything NASA's done in its history. And while I was there, I did what any good intern should do, which is I went and I talked to as many people as I possibly could at NASA headquarters to learn about their work and what they were doing and whether or not there were opportunities in their field, that sort of thing. And while I was doing that, I met Rick, who kind of surprise interviewed me. And I bothered him for several months, keeping him up to date on my graduate work. And I was very interested in Martian exploration. Eventually got hired as a contractor at NASA headquarters. So I've been working on the recon team for just about 4 years now. And let me tell you, it's really fun work. So I just want to give you all a bit of an overview of kind of what we're working on and where NASA's thinking is regarding human exploration of Mars. And some of the opportunities for folks your age to get involved and start helping. So the first thing I want to clear up is that Mars might look a lot like Earth, but it's not all that much like Earth. It looks the picture on the right here is Wadi Rum, Jordan, where they actually filmed some scenes from the movie The Martian because it looks very Mars-like. And on the left is from Gale Crater. Curiosity took that picture. But Gale Crater is a lot less like a desert on Earth, hot and arid, and a lot more like some of the most extreme places on Earth, the tops of our tallest mountains, where the atmosphere is much thinner, there's freezing temperatures. Mars is intense, and we can't go in with the mindset that it's like a desert, even though it doesn't have all that much water, because we'll underestimate the challenge of it. But just like we figured out how to master extreme environments like K2, we'll figure out how to do it on Mars. This is a photo from the top of Mount Everest a few years back, where there's a line. Everyone here has oxygen canisters on them because the atmosphere is too thin to breathe. And maybe we'll get Mars to this level of sophistication one day. But how are we going to do that? Well, we're going to get there by kind of stepping. NASA is all about kind of incremental progress, and that's how we've been doing Mars exploration for the last 50 years since the first orbiter got out there. And you can see this very clearly in our rover design, starting with the first rover on Mars, Sojourner, which was just about the size of a toaster. It rolled a couple hundred feet, took some pictures, and then it couldn't go any further. And then we upgraded to Spirit and Opportunity. They had a lot more capabilities. They both lasted way longer than we ever thought they would. Opportunity just ended its final mission 3 years ago now, when a dust storm covered up its solar panels. In 2012, we launched Curiosity, which is as big as a small car, weighs about a ton, and it has an onboard lab. It has lasers. It's a really cool rover. And Perseverance, although it's about the same size as Curiosity, upgrades further on those attributes. And we're going to do the same thing with Mars missions, starting small and building up our capabilities and the technologies we have available to us on the surface until we have that kind of permanent human presence that we're working towards. And so a human mission to Mars is not a simple mission. It's quite complex, and there's a lot of kind of big pieces that go into it. And so this picture here captures most of the big elements of a Mars mission. You got the vehicle that's going to get you off of Earth. You've got the Mars transfer vehicle, the mothership that will carry you across space between Earth and Mars. You've got the crew cargo lander, which will bring you down to the surface. The rover you'll use to drive around, the habitat you live in, the surface suit you'll use to explore, and then the ascent vehicle to get back up and bring us back to Earth. And each of these pieces has its own unique kind of engineering and scientific challenges. And they aren't all technical challenges. That's something I've really enjoyed learning about as I've worked on Martian exploration, is that there's so many different disciplines that we need to bring to bear to solve this challenge. The Mars transfer vehicle, just as one example, you're going to have your crew living in confined quarters there for 8 months just to get out to Mars, and possibly the full 3-year round trip if they stay in orbit the whole time. And how are people going to behave when they can't see the Earth anymore, when they're cut off from communication and have to wait for messages? It's not the 4 hours you have to wait to get something out to Pluto, but it is a 40-minute delay there and back again at its longest. That's not really a great way to have a conversation. Hello, how are you? And then 20 minutes later, they get it, 20 minutes back. And if there's ever an emergency, the habitat's on fire, 20 minutes there, 20 minutes back, wouldn't do the crew much good. So solving that problem, we need to involve sociologists, psychologists. We need to think about what kind of medicine can we bring with it? What should the crew look like? What are the dynamics there? Can we involve AI researchers to help us kind of facilitate communication, to help make the crew feel engaged? And that's just one piece of this mission. Pretty much all of these pieces have that kind of multidisciplinary aspect. And I think that's one of my favorite parts of this job, is just how many different experts we get to work with all around the world. My team is specifically focused on reconnaissance, as I mentioned. So, and one of our banner projects is the Mars Human Landing Site Study. So this is, where are we going to land the first humans on Mars? Where are we going to build that base? We have a whole planet to choose from, which is a lot in terms of land area. It actually is almost equal with the Earth's land area. If you aren't counting the oceans, just the terrestrial land. And so there's a lot to pick from. And we hosted a workshop back in 2015. We had folks from all across the world propose, where would you want to land on Mars? And we got this map with all of those little circles, or a site that someone proposed. They thought there was enough science and resources there to build a human base. And since this workshop, we've been trying to narrow down the criteria. We know we can't land up at the tallest mountains. We need a lot of atmosphere to slow down a spacecraft as it's trying to land on Mars. And so the lower elevation you are, the more atmosphere you can push through, the slower you'll get. We also know that we probably don't want to land right on the equator. One of the big resources we'll need is water for these missions. And we found subsurface water ice closer to the poles. And so we're trying to use the data we already have access to from the existing orbiters and commission other studies and future missions to help give us a better picture of where the best place to land on Mars is. This is just a ton of an overview of a bunch of the different projects that we help support. Sample return is going to be part of the Perseverance rover's mission. It's the first attempt to take some dirt off the surface of Mars and bring it back to Earth. We're also looking to get a better picture of where the water is on Mars. My job might actually end up looking a bit more like Henry's did on the New Horizons mission in the coming years, as we're gearing up for the upcoming Mars Ice Mapper mission, which will help find exactly where those subsurface water ice deposits are and how big they are. and we want to access them. We want to take more high-res pictures of the Earth, of Mars, get a better weather detection system out there. You know, you don't fly a plane on Earth without checking the weather on here. So why would we try to land a human mission without having the weather report? And then all of these missions are going to create a lot of data. So we need better communications infrastructure to bring all that data back to Earth for scientists and mission planners to pore over. So we have to work on a bunch of different stuff, and all of these different projects engage with academia. We get to work with commercial entities. We get to work with international space agencies. And that's really because Mars, no one country, no one person is going to get to Mars by themselves. It is going to be a human effort, and we need the kind of resources and the creativity of the entire world if we're going to pull this off. And so we try to use that as much as we can. Yeah, so creative partnerships that I mentioned, we're also looking to send more small missions. I'm sure most of you probably heard of CubeSats that are in orbit around Earth, these tiny little satellites. You know, they're cheap and easy to make. They're lower risk for big mission compared to big missions. Let's start using them at Mars. And we even demonstrated that we could do it. We could send a small mission to Mars with the InSight lander. These two CubeSats on the left join the InSight lander on their way out there and help provide landing data as it was making its descent. We work with STEM programs and just like CSO and competitions. A lot of you all on this call are going to be the generation that is landing on Mars. And so we want to get you all involved early so we can take advantage of your creativity. And then I know Austin mentioned you all are, looking for ways to get involved in STEM careers. Some advice that we try to pass on whenever we do these student talks. Probably the biggest thing on this list is to talk to people. I know that might seem kind of simple, but just meeting the folks who are doing the work that you're interested in is the best way to find about their work and what's going on in that field. I think, Henry, I'd be surprised if you disagree, but pretty much everyone at NASA loves talking about their work. It's usually harder to get them to stop talking about their work than it is to get them to start. And you should take advantage of that as students. Pretty much everyone at NASA is excited to help students get involved. And so just reaching out and asking, hey, do you have 45 minutes, 30 minutes to talk about what you're doing? That's a great way to learn about the field and learn about how those folks got involved. Two questions, always ask, who else should I talk to? And is there like anything I forgot to ask? And just keep following that line. And then there's a bunch of other ways to get involved as well. Working in a STEM field and doing research is one way, but there's also opportunities for non-STEM kind of focuses to get involved too. We need storytellers to help us kind of pitch this mission to help make our PowerPoint slides look pretty. To take those beautiful photos that Henry shared of kind of the launches and that sort of thing. There's so many. NASA needs everyone smarts, not just engineers. So yeah. Mars is it's a human effort. We're going to need your ideas, and feel free to reach out. If you want to learn more about the specific work that we're doing, the email there at the bottom is a great way to follow up. We actually do internships in the spring, summer, and fall for university students. So at the next couple of years, you still want to learn more about Mars, hit us up. And with that, I know Austin, and I saw that there were chat things going on, but I didn't.
Great. Thank you so much for your presentation, Bob. I like that we had a presenter representing Pluto and a presenter representing Mars. That's a cool dichotomy that we had.
Inner and outer solar system.
Yes. All right. So now we're going to move on to our Q&A session. So, CISO Sripada, would you like to ask your first question that you had to Mr. Fruit?
Yep, actually I noticed that a lot of spaceships have the gold color on them. Maybe it's just because it's gold color. I mean, like, right? Or is it some kind of material that the spaceship is made of? Or is it just because in space the gold color is more, resistant, or some kind of scientific explanation of why that color is found in many spaceships? I was just wondering.
Yeah, good, great question. Yeah, I don't get that question very much. So, and I'm trying to, as you're asking that, I'm trying to think like, why is it called? So that is thermal blanketing, and so basically, it's a blanket that we put on the spacecraft because the spacecraft has to work when it's near the sun, like at Earth, and then it also has to work when it's at Pluto, which is like there's at Pluto, it's 30 times further away, 40 times further away. So there's 1,000 times less sunlight there. And so it's actually really, really cold. And so we have to have so thermal control on the spacecraft is really important. And so we have to give it insulation. Now we could give it like a down comforter. That would work, but a down comforter is just like too heavy. And so what we actually do is we make a blanket out of many, many layers it's essentially made out of Mylar, and it's coated with metal. And the metal which happens to be easiest to make really thin layers of that are flexible is gold. And so I believe that is why it is a gold blanket, because it's easy, because gold is easy to put in thin layers, and it sticks to anything. It's pretty strong. So yeah.
Thank you. That's
I've actually seen there's a guy who has a sewing machine, and he actually stitches this blanket together, and I've seen them at the lab where they have like all this material, and they've got scissors, and they've got a plan, and he like sits down with his like big industrial sewing machine and like and stitches it out, and then they like bring the spacecraft over and they like wrap it around it. It's pretty awesome.
That's very cool.
That was very interesting. Like the small details make a huge difference to the spaceship. That really made it through. Thank you.
Yeah, you bet.
All right, moving on. Kelly had asked, did the New Horizons spaceship take pictures along the way? Like, was it constantly sending information back to you, or did you have to send a signal to it to like tell it that you wanted a picture for it to send back, or was it constantly taking pictures?
Yeah, so it is not autonomous. Autonomous means it has AI on it to take pictures of whatever it wants to, and there's some spacecraft which we have that are that way. Like some of the Mars spacecraft, for instance, use autonomy to either to move themselves to where it looks interesting, in part, guided by humans. But with New Horizons, it only takes pictures of exactly what we tell it to. And that's because it was designed 15 years ago, 20 years ago, and so now we're getting into the era where you might do it differently. But we only had one chance to go past Pluto, and so we didn't want to take any chances with doing it wrong either, if the autonomy messes up. So most of space is pretty empty, so we were not taking pictures most of the time along the way because there's nothing to see. We basically saw two things on the way. One was Jupiter, and we saw that a year into flight. And then we also passed an asteroid. There was one asteroid, it was in the asteroid belt. And I mean, we passed it like 100,000 miles away or something like that. And that's what's counted as a close approach, is 100,000 miles. And so you could see it as one pixel, one tiny, tiny pixel in the images. And we knew that was there, not because we saw it in the pictures, but because we had a list of all the asteroids. There's 1 million or so asteroids on the list. And so we knew that this one was going to be like, ooh, 100,000 miles away. So let's take some pictures of it. And so what we were taking some pictures, most of the time the spacecraft was sleeping when it was going out to Pluto. We sort of spin it up and put it in hibernation, just like a bear. And then we wake it up just like a bear occasionally to take some pictures and make sure that it's still alive. And so we would go through a calibration sequence every year or so and look at the cameras, make sure the cameras are still performing, make sure the thrusters are still working, make sure all the instruments can be powered on, and see if they're like getting less sensitive or more sensitive, or stuff like that. But most of our cruise was spent hibernating, and the team on the Earth getting prepared for the basically one day of encounter that we had in 2015.
That's incredible. Bob, I have a question for you. What is the Mars Ascent Vehicle? Does that come down with the rover that you sent down? And then how does that work to get the possible people that go to Mars back out of Mars?
Sure. So the Mars Ascent Vehicle it's something we've yet to ever build or test, but it's pretty much just like we have rockets to get our astronauts from the surface of the Earth into low Earth orbit. This would be a rocket on the surface of Mars to get astronauts from the surface of Mars to low Mars orbit. We're going to test this technology for the first time as part of the Mars sample return mission. Perseverance doesn't have an ascent vehicle as part of it, but we're going to send another mission in the next 5-6 years or so. It'll land a fetch rover to kind of collect the samples. It'll load them into this rocket tube. The images of it kind of look like a rocket club style, just launch tube, like a fireworks tube, and then we'll demonstrate the ability to take off from the surface of Mars. And when we do that for a human mission, it's going to have to be much bigger. It's one of the biggest pieces of technology and most complicated pieces of technology that'll be essential to a human mission. And it's got a bunch of interesting questions about it, because we still haven't decided how many astronauts we're going to send down to the surface. If we only send a handful, part of the crew, then we have a smaller ascent vehicle. It'll be easier to get it back up. We also need to consider where we're landing on Mars plays into effect with this as well. You get more energy if you take off near the equator versus the poles when you're trying to launch a rocket. So we don't want to go too high on the planet, otherwise we won't have enough energy, or it'll take too much fuel to launch the ascent vehicle. And I think kind of the last really interesting thing about the ascent vehicle is the goal long term, still, whether or not we do this on the first landed mission is up for debate, but is to have it fueled using fuel that we make on Mars. We can take carbon dioxide from the Martian atmosphere, which there's plenty of. The Martian atmosphere is 99% carbon dioxide, and then H2O and subsurface ice. If we take the hydrogen off of the H2O and the carbon off of the carbon dioxide, we can make methane. And then we have plenty of oxygen to work as an oxidizer. And that makes rocket fuel. Methane combusts as well as anything. And so we want to fuel the Mars Ascent Vehicle with fuel we make on Mars, and that'll help us cut down on the cost of fuel that we need to send from Earth. Yeah, hopefully that answers your question.
Well, that's cool that you can make your own combustion from the area around you to power your spacecraft. That's pretty amazing.
We want to try to do that as much as we can. The less stuff we send from Earth, the fewer rockets we launch off the surface of the Earth, and the more stuff we can make on the surface of Mars is going to help us cut down on the cost of the mission. Usually, the most expensive part of a mission could be just the weight, getting the weight you want to launch into space. And so we don't want to launch tons and tons of water to help support the crew on Mars. If we can instead just have them dig up some ice and melt it, use it as drinking water. Once they're there, it's much simpler.
Great. CSO Chalet, would you like to ask your question about motivation?
Yes. So I was wondering, what motivated you to persevere through all the challenges that arise when working on projects like these?
Yeah, I'll let maybe Bob will answer too, but I'll take it first. I mean, it's fun. There's no, it's cool to do this today. It's cool to do it tomorrow. There's no, if it's not fun, I wouldn't be doing it. So it takes a long time to fly a spacecraft to Pluto, sure. So it takes 9 years to get there, but it takes a long time to build a bridge on the Earth. It takes a long time to build an apartment building too, or a tunnel under a city or whatever. So there's lots of long-term projects on Earth too, and it's really awesome to be part of the team. Most of the team with the New Horizons group, most of that team that started with it is was still involved to some extent out at Pluto, most of the science team. Most of the engineers kind of did their job and then moved on to another mission, but most of the science team was still there at Pluto. And you know, it's cool to work on a team that works together for that long on a really awesome project. So yeah, you know, so much fun, and I hope that you get to work on fun projects like this too.
Yeah, I couldn't agree more. Space exploration is just fun stuff. We get to learn about planets. We get to look at those cool pictures of the surface of Mars, of the surface of Pluto. So like the rewards, the little serotonin boosts we get every time we see something new and exciting, is just so worth it. And then, you know, even when there are challenges, I don't know. For me, that's part of the fun of it. Is we're especially with human missions to Mars, we're trying to do, I mean, this is how it was for New Horizons too, trying to do something no one in history has ever done before. So coming up with the solutions to that and overcoming the challenges that crop up, it's rewarding. It feels purposeful, I suppose.
Yeah, making discoveries for the rest of the world to see, I'd say that's pretty good motivation. Saiba, would you like to ask your question about spacecraft fuel and asteroid collisions?
All right, sure. So my question was like, how do you make sure that when the spacecraft is going to Pluto, that it has enough fuel in order to arrive there without like running out?
Yeah, okay, so here's the deal. The spacecraft, so the rocket itself has like a couple 100,000 kilograms of fuel. So that's the, you know, the big rocket that we launch from, but it spends all that. Like all that is gone by an hour into flight. And then the rocket disconnects and it falls into the ocean, and we go and pick it up with a boat. And then the spacecraft itself is about the size of a grand piano. And it has, you know, a couple 100 kilograms of spacecraft on it, and then a couple 100 kilograms of fuel on it. And so that fuel is basically used just to steer the spacecraft. Like it doesn't change its speed by very much once it's going, but we do use it to steer, you know, turn a little bit left, go a little bit up, you know, whatnot, when we're flying, just to make little minor corrections to our course. And we know exactly how many times we use those thrusters, because that is our one expendable resource. Once we're out of fuel, then we know that there's, I mean, what are you going to do? There's not a fueling station. You can't gas it up again. So fuel is our most precious resource, and we are extremely careful in allocating it. So every time you turn the spacecraft, in fact, it requires fuel. We don't have motors to turn the spacecraft. It requires, you know, using fuel to, you know, rotate the spacecraft this way and then rotate it back that way. It takes fuel. And so anytime you want to do an observation, you have to advocate to the team to say, like, you know, this observation is going to be really important. Now, I know it's going to use 6 grams of fuel, and 6 grams is quite a bit, but, you know, I think it's worth it. And so then we're going to have to do it like a maneuver to go to another asteroid, and that might take like, you know, a couple kilograms of fuel, or, you know, 10 kilograms of fuel. So we started with, I forget the numbers, but maybe we started with 200 kilograms of fuel, and we're down to maybe about 15 kilograms left now. So we've gone past Pluto, and we went past Arrokoth, which is this object in the Kuiper Belt. And each of the, you know, Pluto took the vast majority of our fuel, and then doing the little divert maneuver to Arrokoth took a good number of kilograms. And so if we find other cool stuff that we're going to fly past, like another Kuiper Belt object, that would take more fuel to get there. And then, but we just have to advocate for, you know, what's the value of doing the science versus the loss of the fuel on other science that we might be able to do in the future, and just keep track of that.
Thank you so much.
I have a question about the volcano on Io that you mentioned. So what would have caused that eruption to occur? And then what does that tell you about the composition of the planet or asteroid, whatever it was on? Oh, Io.
Yeah, so Io, right. Yeah, Io is the moon of Jupiter, and we have actually known that it's volcanic for quite some time. We know since it was volcanic since we flew past it with the Voyager mission in 1980. And basically what's going on there, Io is sort of the most volcanic of any moon in the solar system. We've never seen a volcano going off in real time and seen the plume before, well, like, you know, what we did with New Horizons, and that was awesome. And what we think is going on there is Io, so you have Jupiter here. Jupiter's really big. Jupiter's, you know, thousands of times the size of the Earth. And then you have a couple of moons going around Jupiter. You have 4 big ones called Europa, or called Io, Europa, Ganymede, and Callisto. And if you have ever seen Jupiter in a small backyard telescope, you can see Jupiter's moons pretty easily. They're pretty bright. You can see them on a very modest telescope, or even sometimes in a pair of binoculars. And what we think is happening is Io is basically it's sort of dragged, it's sort of in the middle, and the gravity of the moons pulls Io one way, and then the gravity of Jupiter pulls Io the other way. And so it sort of flexes back and forth in the middle. And it's kind of like if you had a big big object here and you flex it like that, then eventually it's gonna one of these objects is gonna it's gonna heat up at the joints and break. And because all that heat goes into thermal heating, and that's actually goes into thermal heating in Io's core, and then all that heat tries to escape from Io, and where does it go? It comes out as in the form of volcanoes, basically. So that's it's made. What we see, we actually see big clouds of this stuff all around Jupiter. It's made of sulfur and sodium. And it kind of is, it's not exactly polluting, but we see the evidence of it all around the Jovian system, all the sulfur and sodium that came out from the interior of Io.
That's really cool. Bob, we have a question for you. With the recent discovery of water on the moon and plans for people to return to the moon, do you think we'd be putting the homemade fuel plan into action there?
So for sure, that is a big motivation for going to the moon is to kind of test out a lot of the technologies we might use for a human Mars mission, and also to kind of build up some of that in-space infrastructure. It's a lot easier to launch something off of the moon, which is 1/6 the Earth's gravity, versus launching it off the Earth. We do have some questions we need to answer before we start making fuel there for a Mars mission, but it mostly revolves around kind of what does the water ice on the moon actually look like? How could we use it? How would we collect it, process it? And is it efficient enough to turn into the kind of the volume of water we need for a Mars mission? We might just kind of do the technology demonstration piece at the beginning to see whether or not we can take ice off the surface of another planet and turn it into methane for fuel. But the water ice on the moon and water ice on the Mars look pretty different based on what we know so far. We think the ice on the moon is kind of mixed up in the regolith. You could just kind of get ice shards with regolith shards. And water ice on Mars, by contrast, it's buried glaciers. When the planet was drying up and cooling down, the oceans got buried, and you just get huge deposits of ice. And so you have different kind of extraction techniques for those different water feedstocks. But in short, yes, we will demonstrate some of the technologies to develop the homemade fuel, as you put it, on the moon.
That would be cool. And also, you mentioned you need a certain amount of atmospheric elevation of the surface to be able to land a spacecraft without it crashing. So what's like the minimum elevation value that you would need to successfully land it?
So again, it kind of just depends on the design of the lander that you use. When we talk about elevation on Mars, we refer to its MOLA, which it's basically like average the elevation, and what is the median elevation, and we call that sea level. There's no ocean, so we have to basically decide where sea level is, and that's 0 kilometers. And then Mars goes up to like 5 or 6. Olympus Mons is way too high, but a lot of like the Martian highlands in the south and stuff are 4 or 5 kilometers. We think that's too high. we're looking at like 1 and below. In some places, it's like down to -2 or -3 in the northern plains, where a lot of the subsurface ice is. It's kind of negative elevation, and so when we're actually working on what will the criteria be for the next human landing site workshop, we're talking in that range of +1 to -2 or so. +1 kilometer, sorry, down to -2 kilometers.
All right, very cool. And Saiba, I see you have another question in the chat. Would you like to discuss that one?
Sure, thank you. So I actually did type one in earlier. I'm not sure if it didn't send through, but I was wondering, like, since space is pretty empty, and you were mentioning that it's not likely that we'll hit an asteroid on the way to Pluto, but what would you do if there was an asteroid that was like in the path, or that it collide with the spacecraft?
Yeah, so I mean, the odds against it are really, it's kind of like 1,000,000 to 1 that there would be anything that was anywhere near us. But in the event that there was something, so if there was something, let me answer that in 2 ways. If there's something that we knew ahead of time, like if we knew, a month ahead of time, then we would just, do a little divert maneuver instead of going like that way. We would go like, we would, just kind of turn out of the way and then get back on track. If we knew that something was coming because, we saw it right coming at us, well, that's actually a little bit like what we were doing when we were heading toward Pluto, actually, because I said that we were looking for dust which was on the surface, or which was kind of in the region of Pluto, because we're going so fast that if we would have hit a dust particle, it would have, been the end of the mission. If it's, a couple of millimeters across, would have ended the mission. And so we can't see an individual dust particle coming at us. And if you, normally your camera isn't pointing forward, because that's, there's lots of directions to look, and forward isn't always the best direction. So you wouldn't necessarily really see something that's coming at you. And if you do, it might be too late. But if you, what we did look for at Pluto is like clouds of dust that might be in the Pluto system. And we actually had a team whose job was to monitor and see if there were clouds of dust that looked like they were in the region of Pluto. And if they did see any, then we were going to divert past Pluto and basically not take our best images of Pluto by going, here's Pluto and here's the spacecraft. And our best plan would be fly right past the spacecraft like that. But if we saw some dust clouds there, what we would have done instead is go over here and do a distant flyby of Pluto instead, just for safety.
Yeah, thank you for answering that question. That's really interesting, and I think how like the timing is really important. That's also a really major factor. The other question I had was that, so personally, since I think about 5th or 6th grade, I was interested in doing something related to space. I just wasn't sure exactly what. So by now I've narrowed it down to like computer scientist. So I was wondering, does being a computer scientist at NASA, what similarities would there be also in being an astronaut, astrophysicist, or astronomer?
So totally different areas. Most of the computer science, there are a lot of computer scientists and computer engineers and software engineers and IT people who are involved in a lot of the NASA projects. And most of that is kind of, most of the computer science stuff is more on the engineering side. And most of the, if you're doing astrophysics, that's more on the science side of things. And so, like, if you're doing research and writing papers, that's more on the astrophysics side, and using telescopes, using data which you download, and kind of trying to understand the physics of what's going on. Like, astrophysics, or what I do, planetary science. Like, what caused this planet to be this way? What caused this star to be this way? Why do galaxies do this? That's kind of what you do on the science side. And then on the computer science side, then most of that is like, okay, we have, this telescope data. How do we process it so that everybody can make it available on the web and download it? Or how do we get it from the spacecraft into a form that everybody on the ground can use efficiently and quickly, and stuff like that? So it's kind of more of a general skill, or general, doing on the computer science side of things, versus versus doing the science on the astronomy side of things. And all those are really fun and really valuable. And like you should go wherever you think the most fun is, because you'll do a great. That's where you'll be the best and the most awesome at doing what you want to do.
Thank you.
We need computer scientists for Mars too. Once, as I mentioned, with the communications delay, we won't be able to have that kind of constant back and forth that we get on the ISS. And so we need to figure out how to automate a lot of those functions and systems so that the astronauts can operate independently. And that is a computer scientist job to develop the intelligent systems, as we refer to them, to help keep our astronauts and the crew vehicle kind of operational while it's away from Earth. So.
And Bob, isn't it right that like on the Perseverance rover, that has a lot of AI on the rover itself, where it's doing like figuring out like, oh, I want to go from here to here, but there's a rock in the middle. How do I actually drive my wheels to get to that place? Is that right?
Oh yeah, because we don't get to talk to Mars as much as we want to, especially the rovers, we try to make sure that the rovers can operate without constant input. And a lot of that has been pathing, trying to figure out where it could go. We say, go to this place, and the rover has to figure out how to get there. And that's only going to become more important as we build human class rovers. So if the crew lands off target, they don't land where we expect them to, we just tell the rover, go pick up the crew. And we won't need to have a joystick there to drive it across the Martian surface. We need AI to help us do that.
Great. Well, this was a great discussion, really fascinating on both sides. Thank you both for presenting. Do we have any more questions? Because that's all from the chat that we have so far. Oh, all right, there's one. So Saiba asked, what kinds of classes or opportunities would you suggest to take up in high school or be on a good path for something related to NASA or a computer scientist? So just the education path, and how would you get to NASA if you actually wanted to go to NASA?
Go for it, Bob.
I mean, part of my talk is, about how many different ways you can get involved with NASA. I think Henry's advice of following your passion, what excites you, is probably going to be the best way. Even though my work isn't super technical, having some, I took astronomy classes in college because I liked it. That helped. But there's not like one course catalog you should pursue to get a job at NASA. It's really going to be more about being persistent and finding that niche where you can really demonstrate your skill set.
Yeah, it's such a diversity of skills and of people and of things that people work on, and like doing the stuff that is most fun for you is what you should do, because it's what you're going to be the best at, because that's what you're going to enjoy doing the most. Because if you want to do it as a job, you may as well have something that you love doing. So figure out what's most fun and just keep doing that.
If I added something to that, it would just be don't wait for the perfect opportunity. If I want to be a computer scientist working on Mars rover technology, that job listing might never crop up. But if you find computer engineer or software engineer at a NASA center, jump at that. take the first step that's in the direction you want to head. Because it is way easier to find out about job opportunities or make the job come into existence once you're at NASA, rather than waiting for the perfect opportunity to come around, because it might not.
And take those other opportunities, like working at your neighbor's accounting firm, or working at your the internship at the whatever center down the street. Like all these things, whatever you do something cool, do something which take these opportunities whenever given the chance, even if they are completely apart from what you think you might end up doing, because you get something out of everything.
Yeah, I agree. Thank you for sharing. And I agree that like you follow your path and your dreams to make things happen, like just like the CSO slogan says.
I agree. And Kelly asked, how are internships working now with the remote work? Are you guys still offering them? How would you apply?
Yeah, so we're still steaming ahead. We had interns when we went into lockdown, and we just kind of transitioned to virtual. Since most of our work at NASA headquarters can be done virtually, we don't work with hardware, so you can send an email, join a meeting from pretty much anywhere. So all of our interns are virtual. It's actually made it a bit easier for some of them because they don't have to move to DC and try to find an apartment to be able to do the internship. And yeah, NASA adapted pretty well to the remote environment. If you're looking to apply, the best place to go is interns.nasa.gov. There are opportunities for both high school students and university students. Most of them are targeted towards university students, but I know there are some summer high school opportunities. And then if you want to intern with us from our stuff, emailing me is probably the best way to figure that out. Yeah, and like talking to people at NASA and learning about their internship opportunities is another good way to do it.
Excellent. And what are you both working on currently? What exactly are you doing right now with your jobs?
Go first, Henry.
Okay, let's see. One of the things, though, I am not, working flying the New Horizons spacecraft right now or anything like that. But what I am doing is I'm running a lot of the science programs at NASA headquarters. So that means that NASA does science. Some of the science NASA does itself, but most of the science that NASA does actually by giving money to universities and having universities do this. Like the university will build a spacecraft, which is what the New Horizons one was actually. It was Johns Hopkins and a place called Southwest Research Institute. It wasn't actually NASA that built the spacecraft. It was NASA that funded the spacecraft, but they gave the money to a university and another group to build it. And so I'm in charge of running a lot of the research programs. So if a university or a person or a group or whatever wants to research something about Pluto or something about Saturn or something about Jupiter or something about Uranus, I'm the person who runs most of those research programs. So they send they type a little proposal saying, hey, I want to research Jupiter's rings about, and I want to do a 3-year project about such and such on the rings and all that. So they send a proposal in, and then I run the process that reviews those proposals and then figures out which of those groups we will send money to. So that's really fun because it's a nice way to interface with the community and make sure that the science that all the scientists in the U.S. think is really cool, make sure that we want to figure out what the best science is and make sure that those groups get funded. And then eventually that kind of leads into knowing more about the solar system, and then that leads to future missions. So that's what I was doing last week, is I was talking with a lot of people who were reviewing proposals, and we were kind of getting their opinions on all these proposals so we could figure out what the best ones were and make sure we fund all those people.
And on my side, I'll probably spend most of the next week getting our spring interns up to speed on the various projects. And other than that, the big thing on my team's plate right now is the International Mars Ice Mapper mission. Since we're at headquarters, a lot of what we do is trying to get the right smart people in the same room talking to each other, virtual room, as it were, at present, and building a mission. We're at the very beginning of it, doing the initial studies into what should the spacecraft look like? How much power does it need? Can we launch anything else with it? Those sorts of questions. We're organizing those meetings, getting those people talking, help review their work, and seeing if anyone else wants to get involved. We do a lot of international coordination, so just trying to keep everyone up to speed on the same page and make sure that we don't miss any opportunities for NASA to jump ahead in our Mars exploration plans by collaborating with someone cool.
That's awesome. Good luck with both of your progresses. Hopefully we can hear your names in the future again with more discoveries.
Thanks very much, Austin. It was great to be here.
And I think that all the people on this call, we will see your names in the future discoveries too. There's so many good questions, so many good engagement from all of you, and such a good program. So best wishes to all of you, and thank you.
We appreciate you being willing to coordinate with Austin as well. It's really important that everybody on the call understands it's a student-led program and it's about defining their own leadership. And I really liked a variety of different things you both shared about just try it, take your path. You don't have to, you just know a general direction. I was going to ask Bob if you had a cat, if you were going to show us.
He loves to jump us.
They can visit.
I kept hearing it. I was
Lord
like,
bless.
oh my goodness.
Squirmy. She did not like that I was paying more attention to the laptop than I was to her.
Aw.
Kristen, you guys, I had no idea. I could hear her though.
Oh, was she
they're all
purred
close
close
the
enough
same
to the
looking,
mic?
too. They're like twins.
They
Little
are. You
cat
guys
too.
all have like the same cat.
That's been a real plus for working from home. Never too far from a cat.
Yeah. I just have become a dog owner. All the CSOs know that it's like I've never had a pet really in my later here in life. And so I just am so smitten with my puppy dog. But I wanted to give Austin a huge shout out. He did take the initiative to contact you both, to coordinate with you both. And I thank you for spending your, day with us today, especially when it's a day off in honor to commemorate Dr. King. So thank you for that. And you were both very exciting and very personal. So I really appreciate both Austin, who is representing Pennsylvania, all of the CSOs who joined, and all of those that are on the call specifically to watch Austin really do an incredible job as the host. So again, thanks, Bob. Thanks, Henry. Thank you to everybody for joining us tonight. I will be sharing the video so you can share it potentially if you wanted to show it in, another group. This was an incredible call. So thank you so much. Austin, final thoughts? You can close us out.
Thank you both. I'm glad that we could connect you to the CSO program, and hopefully we'll see you again in the future. But thank you for your presentations. We all enjoyed it and we had some great conversations. So thank you.
Thanks, everyone. Bye.
Thank you. See y'all.
CSOs, don't just hope it happens.
Make it
They
happen.
make it happen.
Happen.
Good night, everybody.
Woo. Good night.